When we examine carbon in detail, we see that not only the formation of this atom, but also its chemical properties have been specially determined. In nature, carbon is found in two separate forms, graphite and diamond. However, the compound it forms produce very different substances. All the very different organic structures, from the cell membrane to tree bark, from the lens of the eye to a deer's antlers, from the white of an egg to snake venom, all these consist of carbon-based compounds. Carbon combines with hydrogen, oxygen, and nitrogen atoms in very different geometrical forms and sequences, thus giving rise to very different substances. Some carbon compounds consist of only a very few atoms, while others contain thousands or even millions. Only carbon atoms can form such long and permanent compounds. In his book, Neville Sidgwick says this about carbon. Carbon is unique among the elements in the number and variety of the compounds which it can form. Over 250,000 have already been isolated and described, but this gives a very imperfect idea of its powers, since it is the basis of all forms of living matter. When carbon combines with other atoms to form organic compounds, the bond established between the atoms is known as a covalent bond. Covalent bonds are formed when two atoms share the same electrons. Electrons revolve in specific orbits around the atomic nucleus. There may be only 2 electrons in the orbit closest to the nucleus. The next orbit may contain 8, and one after that 18, and so on. The noteworthy point is that atoms have a predisposition to make up the number of electrons in their orbits. For example, oxygen with 6 electrons in its second orbit wants to add another 2 electrons, and thus complete the orbit with 8 electrons. No answer can be given to the question of why atoms have such a tendency, but were it not for that predisposition, life forms could obviously never come into being. Covalent bonds are formed thanks to the atoms' desire to complete their orbits. 2 different atoms that want to complete their orbits do so by sharing their electrons. The 2 hydrogen atoms and 1 oxygen atom that constitute water, for instance, build a covalent bond. The oxygen raises the number of electrons in its second orbit by sharing 1 electron with each of the hydrogen atoms. Each of the hydrogen atoms raise the number of electrons in its second orbit to 2 by using 1 of the oxygen electrons. Carbon thus gives rise to very different substances by building such covalent bonds. Methane is one of these substances. The formation of methane comes about by 4 hydrogen atoms building a covalent bond with a carbon atom. Since the atomic number of carbon is 2 less than that of oxygen, the carbon bonds with 4 hydrogen atoms instead of 2. As we said at the beginning, the bonds built by carbon constitute a very wide spectrum. The bonds that carbon establishes with hydrogen alone give rise to the large family known as hydrocarbons. This family includes natural gas, liquid petrol, fuel oil, kerosene, and various machine oils. The hydrocarbons, ethylene and propylene, are the basis of the petrochemical industry. Other hydrocarbons give rise to such compounds as benzene, toluene, and turpentine. The mothballs we put in cupboards to protect our clothes against moths contain another form of hydrocarbon. Hydrocarbons that combine with chlorine or fluorine produce such different substances as anesthetics, fire extinguishers, and the freon used in refrigerators. The covalent bonds that carbon builds with hydrogen and oxygen represent another wide spectrum, including alcohols such as ethanol and propanol, as well as aldehydes, ketones, and fatty acids. Two important substances formed by carbon, hydrogen, and oxygen compounds are the glucose and fructose in the foods we eat that provide us with energy. Cellulose, the constituent of the hard part of trees that represents the raw material for paper, beeswax, vinegar, and formic acid, again form as the result of the covalent bonds that carbon constructs with hydrogen and oxygen. When carbon builds bonds with hydrogen, oxygen, and nitrogen atoms, very important compounds once again result. The most important of these are amino acids, which form proteins, our body's building blocks. The nucleotides that make up DNA are also molecules made up of carbon, hydrogen, oxygen, and nitrogen. In short, the covalent bonds constructed by the carbon atom are among the most essential preconditions necessary for life. If carbon were unable to build covalent bonds with oxygen, nitrogen, and hydrogen, then life could not exist. What enables carbon to form these bonds stems from a characteristic chemists refer to as metastability. The well-known biochemist John Burden Sanderson Haldane describes this feature as follows. A metastable molecule means one that can liberate free energy by a transformation, but is stable enough to last a long time unless it is activated by heat, radiation, or union with a catalyst. This technical definition means that the carbon atom has a very unique structure, thanks to which carbon is easily able to form covalent bonds under normal conditions. However, there's one very interesting point here. Carbon's metastability, which is essential for life, only applies within a very narrow temperature range. Above 100 degrees Celsius, carbon compounds become highly unstable. We all observe this in our daily lives. An example of this is when we cook a piece of meat. Cooking it is actually changing the structure of the carbon compounds. One important point needs to be emphasized. The meat that is being cooked now becomes entirely dead. In other words, it assumes a completely different structure to that in a living organism. Most carbon compounds decay at above 100 degrees Celsius. Many vitamins break down at once. Sugars undergo structural change in the same way and lose their nutritional value. At a slightly higher temperature, 150 degrees Celsius, for instance, carbon compounds start to burn. In other words, the upper limit of the temperature range for carbon compounds to establish covalent bonds and maintain these in a stable manner does not exceed 100 degrees Celsius. At a temperature lower than 0 degrees Celsius, however, organic biochemistry becomes impossible, yet other compounds are different. Most inorganic substances are not affected in this way by temperature changes. In order to see this, you can place some metal, glass, or stone in a frying pan next to a piece of meat, and then heat them up. You'll see that as the temperature rises, the structure of the meat changes, it darkens, and eventually burns. Yet nothing happens to the metal, glass, or stone, not even if you raise the temperature by hundreds of degrees. Close inspection shows that the temperature needed by carbon compounds in order to build and maintain covalent bonds is exactly the range that exists on Earth. Yet, as we have already said, the temperature in the universe as a whole vary from the fierce heat of millions of degrees inside the hottest stars to absolutely zero, or minus 273 degrees. Yet the Earth created for human beings possesses just the temperature range required by carbon compounds, the building blocks of life. One more striking aspect of all this is that the temperature range is also one which water assumes a liquid form. As we saw earlier, water, one of the essential preconditions for life, needs exactly the same temperature range as carbon compounds. Yet there is no natural law that makes such a harmony necessary. This is an indication that the properties of water, carbon, and the earth were created to be compatible with one another. The flawless nature of Allah's creation is revealed in the Quran. He who created the 7 heavens in layers, you will not find any flaw in the creation of the All-Merciful. Look again. Do you see any gaps? Then look again and again. Your sight will return to you dazzled and exhausted. Covalent bonds are not the only bonds that keep the atoms in the living body together. There is a second class of bonds. These bonds of different kinds are collectively known as weak bonds. Proteins, basic building blocks, owe their complex three-dimensional shapes to weak bonds. In order to clarify this, we now need to touch on the structure of proteins. Proteins are generally referred to as amino acid chains. This is an accurate definition, though an inadequate one because the term amino acid chain calls to mind a two-dimensional series, like pearls strung out one after the other on a necklace. However, the amino acids that constitute proteins have a three-dimensional shape, like the leaves on different branches of a tree. Covalent bonds keep the atoms that comprise amino acids together. Weak bonds, on the other hand, combine amino acids together in the requisite three-dimensional form. Were it not for the weak bonds, proteins could not exist, and there could be no life in the absence of proteins. The noteworthy aspect of this is that the temperature range required by weak bonds is, as with covalent bonds, exactly the temperature range that exists on Earth. Yet weak bonds and covalent bonds have completely different structures. And there is no natural reason why they should both require the same temperature. Nonetheless, both classes of bonds are established at the same temperature. If covalent bonds were stable at a different temperature than weak bonds, then protein building would be impossible. All of this information about the extraordinary properties of the carbon atom shows that there is enormous harmony between this atom and other atoms and compounds that are the essential building blocks of life, such as water. There is also harmony between the stability of this atom to form bonds and the temperature of our planet. Our planet provides a home for all these elements and compounds. Michael Denton emphasizes this fact in his book, Nature's Destiny. Out of the enormous range of temperatures in the cosmos, there is only one tiny temperature band, in which we have 1. Liquid water, 2. A great plenitude of metastable organic compounds, and 3. Weak bonds for stabilizing the 3D forms of complex molecules. As we have already seen, this narrow temperature range exists solely on Earth among all the known heavenly bodies. What is more, carbon and water, 2 of the main building blocks of life, are found in large amounts on the Earth. All this goes to show that the carbon atom and its extraordinary properties were specially created for life, and that the planet Earth was specially created for carbon-based life.